Okay, we're going to spend some time today talking about Chapter 8 in our textbook. So, I want us to recognize first off that in terms of our thinking about this, we can break this into three neat little nice little packages. Okay? There is going to be the operator console, the high voltage generator, and then the X-ray tube. These are the three main components of any X-ray imaging system. Okay? Our textbook does a good job of defining these things that are in these various sections. So like figure 8.1 in our textbook, we're going to look at a slightly different version of that. And we'll kind of break that down just slightly differently. But looking at, if I was to compare this slide with what's on figure 8.1 on page 134 in our textbook, we have Kvp Selection on in the operator console. If you want to look, it's B on this illustration here that has the little auto transformer there, where it has a single winding. That's where Kvp selection will occur. And so it's helpful to know that that's not wired up to any high voltage, right? So I could set my coffee cup on the operator console and accidentally spill it, and I'm not going to fry myself down to the fillings. I'll still electrocute myself to death, but it won't just be fillings left, right? So my wife can have some consolation there. So within the operator console, things are not at a high power yet, is what I'm saying. So the Kvp selection, the MA selection, the time selection are all within that operator console. They're not wired to any high voltage electricity. Moving over to anytime, so high voltage generator, step up transformer, right? That sounds dangerous to me. If you have a transformer that's stepping up power, it's doing significant work. And so on this illustration on figure 8, that's E, the step-up transformer. And he may have spent some time talking about turns ratio and stuff like that. The important thing here is that there's more secondary turns. It's stepped up the number of turns. So if you look even on that illustration, it's got a number of windings around that core. The windings on the first side, the left-hand side, are less than the windings on the right side, that secondary side. And so a step-up transformer has more windings on the secondary side. That is what a step-up transformer is by definition. So we can look at that mathematically, but I like the picture. The picture is very clear, right? So it's going to step up the power. And also within that circuit we have the rectification. That's indicated as G on that illustration. This is a series of diodes that allows power to only flow in one direction. And finally, the last step is the X-ray tube itself. And it is going to be on what we call the filament circuit. And so if you can see, that's illustration K on figure 8.1. That is a step-down transformer. And so it has less secondary turns. It's a step-down transformer, so there's less turns on the right-hand side. Can you see how the wire has less windings on the right-hand side? That's important. That's important. So one of the things I want y'all to recognize is there's important safety considerations here at each step. There's important patient care considerations at each step. On the operator console, I've said it is not wired to high voltage, so that's a safety consideration. I don't want my text to be electrocuted, right? With the high voltage generator, it steps it up so that I can produce high energy X-rays. That's also a safety consideration. I want these X-rays to be of sufficient energy to produce diagnostic quality X-rays, images, right? Then finally, within the X-ray tube, we have a step-down transformer for that filament circuit. And that step-down transformer, again, provides to make sure that I'm not going to blow the X-ray tube out, right? So it's helpful to package these things up. Now, I want you to understand something. The way that we're going to talk about the electrical wiring of the X-ray tube is kind of like, I don't know if y'all remember, did anyone ever have Fisher-Price toys when you were a little kid? Did anyone have the Fisher-Price record player where it was like this plastic disc and it had like actual little pokey things on the disc and it would make some, like, Mary Had a Little Lamb song? That's a really, really, really basic idea of how a record player works, right? This is like the Fisher-Price version of an X-ray tube. The reality is, and we'll pull some of them out, we'll look at them here in a minute, is they're much more complicated animals than this. So you might ask, well, why are we looking at this then at all? Again, it goes back to safety and patient care. Everything that we're talking about today, I'm going to relate back to imaging considerations. Here, this comes from Stuart Bouchong's book, which I was raised on Stuart Bouchong. I'm a big fan of Stuart Bouchong. It's only been this year that I've fully adopted this textbook, so I still really like his illustration of the X-ray tube circuit better than the one that's in our textbook. So I've included this here. And what I like again about this is it shows me where the control console is, the high voltage section, and the X-ray tube. And it allows me with just a little bit of inspection to look at this and to see how these different parts work. So what we've got here, starting from left to right, is this section here is just a plug. It's some kind of power source, right, that's coming into the hospital, let's say, or that we plug the X-ray tube in. The first thing that we come to is a line monitor. The line monitor works alongside the line compensator, and the way that I explain this to students is this is the thing that if a raccoon falls into the power transformer down the street and you get that boom in the power like that and everyone kind of freaks out, like is the power going to go out or not? That surge in electricity, that change in potential, is taken care of by the line monitor and the line compensator. So it basically prevents those kinds of those little speed bumps from damaging the equipment. That's what these compensators do. There's also natural changes in the power itself. So let's say Pickwick Dam is a little bit down right now and the turbines aren't spinning quite so much, so we're not getting all the cycles of electricity that we would want. It can compensate for that as well, right? So it's going to compensate because we want a fairly steady amount, fairly pure kind of energy, electricity coming into this system, okay? The next thing, moving from left to right, is the auto transformer. I should point out this is the only transformer that has a single winding. So it works off of what we call self-induction. It works off of self-induction. I'll say that one more time. This is really important. The auto transformer, one winding. One winding, it works off of self-induction. So you might be wondering, well, why do we have this auto transformer? What is it doing? Well, it allows us to set the KVP, right? So it steadies the power going in with the line compensating going on down here. Here on one side of the auto transformer, it's steadying the power, and on the other side of the auto transformer, it's allowing me to select the KVP. So the KVP selector is wired directly to the auto transformer. It's within the control console. If you go into the Honeymoon suite and you start to mess with the KVP, you'll also see a KVP meter that moves the needle back and forth as we select KVP. That's exactly what's happening, and I'll show you the wiring for that in just a minute. Okay. Strangely enough, close tied to the KVP circuit, there's also the timing apparatus here. Let me do that one more time. This timing apparatus here. So you might be wondering, why is the timing apparatus tied to KVP when we normally talk about as mass, right? Milliampere seconds, right? Hold that thought. That's a really, really good question to be asking. But let's continue down the line. Also within the control console, the final thing that we're going to have in there is the MA selector, right? This works very similarly to the KVP selector. Their difference is the kinds of transformers that they then place the power within. The KVP is going to, again, what kind of transformer? We said it has more windings on the right-hand side, so what is that? That's a step up, so I'm just going to draw an up arrow, right? Over here I've got less windings on the secondary side, so what's that? Step down, right? So we step up to kilovolt peak. We step down to MA. And one of the reasons for that, again, is we're stepping down to power the X-ray tube. So this MA selector is going straight into the tube, right? This power here. I don't want to skip over it, and this is going to be very important when we get to image eval, but this focal spot selector, we've not yet got quite enough information to talk about it fully. We will be coming back to it, so just put a little star next to it. The focal spot selector allows us to choose different focal spot sizes, whether it's small or large. So just file that away, we'll be coming back to it. It's not something I'm going to test you on right now. If I go upstairs to the KVP side of things and the step-up transformer, it does some weird stuff, but this section right here is a rectifier. And like I said, it allows the energy to only travel in one direction. This is fully talked about on page, I think, 134 and 135 in our textbook, the process of rectification. So the alternating current now needs to be rectified. And if I come up here, when I talk about alternating current, I'm talking about a waveform that looks like this, right? This rectification system is only going to allow the electricity to flow in one direction. So essentially what it's doing is it's getting rid of the sections down here, right? That'd be one level of rectification. If we go to the next level of rectification, it then flips it over the line, right? We could even further rectify it to where it's producing something more like this, where it has things in pulses or in sequences. Okay, so we're going to look at that in just a second, but I want you to be aware that's what this guy is doing right here, the rectification. Now, where things get weird is it also has the MA meter, right? So the MA meter is one of the few readouts that's in that high voltage section, right? And you'll notice when you're changing the MA meter on the machine, it goes boom. It does that weird little thing sometimes in the honeymoon suite. That's because you're actually affecting the high voltage circuitry, and you'll even see the KVP change, right? So we'll look at that some more. But what this high voltage section here is doing in terms of the upstairs part, the kilovoltage side, is it's stepping up the potential, right, into the kilovolt section of potential so that it can pull those electrons across the tube and generate a whole lot of power, right? So I said the timing circuit though. So the time part of it is how long is that going to be energized? Because that's going to be what determines the amount of electrons that jump across, is how much time have I given it this potential. So when the time stops, the potential stops also. So the electrons jumping stops. Okay? No, I just told you a whole lot of weird sounding stuff, right? We are going to drill this down today. Okay? So I'm going to move forward, but it's not going away. So here again in review is the way that I think about the circuitry of the X-ray tube. I think probably the best thing that you could do with this slide is just in your notes or using your textbook, make flashcards for each and every one of these points. For control console, line monitor, auto transformer, and just detail what they are. You can draw pictures of them, whatever you want. But each one of these things we need to be able to define. Okay? So the control console, it is a low voltage section. It allows me to control the equipment without being significantly electrocuted, right? Within it, I have a line monitor that monitors the amount of electricity coming into the circuit. That runs right into an auto transformer, which has single winding, and it works off the principle of self-induction. Also related to that is that line compensator that's wired back to the line monitor that allows the machine to compensate for changes in electrical power coming to the machine. There's a Kvp selection that is tied directly to the auto transformer, and it just selects the number of windings that are activated on the auto transformer. That MA selection is going to come off of that and have its own separate section in the high voltage part. The timing section comes off of the Kvp selector. On the high voltage side, the step-up transformer goes to the Kvp part of the X-ray tube, so it's step up to kilovolt peak. It has more windings on the secondary side, the step-up transformer does. The rectification circuitry allows power to only flow in one direction, so it prevents alternating current from entering the tube. The MA meter is on that high voltage side. It's very important to remember that's where it's located, because the MA controls directly affect the high voltage, the kilovolt peak. And then finally the X-ray tube. I think it's more accurately to place it within the filament circuit. After the step-down transformer, that powers the cathode portion of the X-ray tube. And the focal spot selector, I said, we'll wait just a little bit on that, but it has a small and a large focal spot. We'll talk about why that's important and those different filaments that are related to that. Okay? All right, I'm changing gears here. This is, so we're hitting a bunch of stuff today that students tend to struggle with. Almost every single slide in this presentation is very carefully selected, because this is all stuff that's super important to how X-rays are produced. You may not be able to imagine how this relates to anything right now, and that's fine. I wouldn't expect you to. But all of this stuff has a direct bearing on the type of images that we're getting, right? And these are all fairly academic things that students struggle with, okay? So let's talk, I'm changing gears now to talk about voltage waveforms. This is that weird little squiggly line, revised, okay? In our textbook, the best illustration of it is on page 139. We're talking about X-ray generators, how these generators control power. We've said that alternating current is what is produced from our electrical generators, right? It also is how we can control motors. So it is useful. It's very, very useful. But it is not useful. It is not the kind of power that we want for the inner workings of the X-ray tube. We need a direct current or something very close to it for the X-ray tube, because we only want the electrons to hop in one direction, and that is from the cathode to the anode. Okay? So we're going to have to rectify or correct the power frequency before it comes into the X-ray tube. So when I asked you, what is the frequency of power in the United States of America, and we said it is 60 hertz, that means it has 60 cycles per second. Okay? 60 cycles per second. And each cycle, we've said, looks like this. It's an alternating waveform. I slightly misdrew that. Just a sec. Let me draw it right, because this is important. So that would be one cycle of alternating current, and we said that there is 60 hertz. That means there's 60 of these cycles every second in U.S. power. So if you take your blow dryer to Europe, number one, you won't be able to plug it in because their plugs look different. But if you were able to plug it in, you would blow it out because they use a totally different cycle. The power might be the same, cycles are different. Okay, and that's important. So we've got to fix this cycle somehow. There's a couple of different ways we could do that. One of the first ways we have is self-rectification or half-wave rectification. And that is this first step right here. Half wave would look like this. It would just be bump, and then there'd be a little space, and then bump. Because I wasn't able to get this part down here. I wasn't able to flip it over the line, right? I was only able to correct half of the cycle, right? It has 100% ripple. That means that from this point right here to the top of this waveform right here, all the range of energies of X-ray production are possible. Everything from 1 kiloelectron volt up to whatever I set. Let's set I set 100 kVp. I will produce, if I have my machine set up like this, 60 times a second, I will produce an X-ray or a series of X-rays that have either 1 kiloelectron volt or 100 kiloelectron volts. Now that's a problem, right? Because I don't want to make an image that way. A certain percentage of the photons that I'm making would just be irradiating the patient and have no promise of making an image, because that's 100% ripple. One way to think about what I'm talking about right now is like a rainbow. Okay? We all like rainbows, they're pretty. When you turn on the X-ray tube, you are making rainbows, right? You're making a spectrum of energies. Okay? It's my very bad drawing of a rainbow there. Looks sad, I know. When we talk about kilovolt peak, we're saying we're going to set a technique up here, and that's the peak energy. The peak energy of my rainbow, right? It's the top of the kilovolt peak. But there's all these other energies beneath it. We want to minimize those other energies because they're inefficient. I would love it if when I set 100 kVp, every X-ray that exits that tube is 100 kVp, because I could be that much more scientific in my technique, right? So half wave is out. All right, well let's rectify the full entire wave. That means we're going to flip that negative portion of the alternating current up over the line. So now I've got something that looks like this. Bam, 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 bam. That's better, but what's my ripple? It's still 100%. I still have every possible, and now I'm just making them more often, but I've got all these inefficient X-rays that are not doing the kind of work that I need them to do. Okay? So the way that we're going to fix that is rectify the pulses. Okay? And this is illustrated very clearly on figure 8.10 and figure 8.11 in our textbook. So for 3-phase, 6-pulse, what's actually occurring is very clearly illustrated on figure 8.11. It is phasing out the power. So now I don't just have one waveform entering the machine, I have 3 waveforms, right? I've got 3 waveforms entering the machine. So as one of them starts to fall off, the next one's pitching into action, right? And I'm also pulsing those guys, right? And what that means is the waveforms, they're out of sync, and I'm also pulsing them 6 times, which again, I'm just flipping them over the line, right? So I've just doubled and then doubled down on the process. So this is fairly difficult to draw, and I don't really have space to draw it here. I am going to draw it right here. So I've said I'm going to flip it over the line, and I'm going to say that's my pulsing there. But I'm also going to have 3 phases of this. So now I've got one that starts right here. And it's going to have the same spacing to it, but it's going to be slightly out of phase with the other one. And now I'm going to start another one right here. And it's going to be slightly out of phase again. Right? That's kind of a confused mess right now. But what the machine is getting is something more like this. Right? So what I've just done is I've just allowed for this to occur. Can you see that? So I can say that for this 3-phase 6-pulse machine, I only have 13% of ripple. Right? For 3-phase 6-pulse, that is, by the way, the Honeymoon suite. It has 13% of ripple. And we will do experiments this fall, and you will, or in the spring, and you will see that that actually has a major influence on the kind of technique that you can set on that room versus the high voltage room, the high frequency generator room. Okay? So this has a huge bearing on the quality of x-rays that are being produced by the x-ray tube. Okay? This rectification process. I won't belabor the point anymore, but to say that 3-phase 12 pulse just has that many more pulses to it, so that we've doubled it down yet again. We're going to decrease the ripple to 4%, and when we get to the high frequency room, like the presidential suite, that's less than 1% ripple. Okay? We can see an illustration of what that type of waveform might look like on page 813. Yeah, 140 and 141. That's correct. Those demonstrate the high voltage, and so what we're seeing now is something more like this. This is as close to direct current as we can possibly get, in other words. Now, it is helpful to know that some of the x-ray machines that we work with are direct current. Your portable machine runs off of batteries. Batteries use DC current, right? So what's interesting is in terms of these considerations, the best pictures that you can get are going to be with the portable machine every time. It is the most efficient x-ray producer, right? So portable is your friend. It's a very, very powerful, very, very useful machine, and it does not have any of these needs for rectification because it's running off of batteries. So if I was shooting in the Honeymoon suite and I moved over to the portable, I would need to significantly change my techniques, right? That may not seem like much of a consideration right now, and it's not, frankly, because most of what we're shooting on is high voltage or high frequency generators. But in the past, it was a significant difference. We had to have separate technique charts for our portables and our machines in the department for just that reason. We will come back to this. It's an important thing. It's not going away. Here's yet another way of thinking about it. And you can see it's just a drawing very similar to what I drew with the nice little neat red lines there showing you different percentages of ripple. I would say those numbers are worth memorizing. I know it seems really arcane and weird, but I've seen registry questions related to this. And what they want to make sure is that you understand is that these processes do affect X-ray energy exiting the X-ray tube. Okay? So at some of our clinical facilities, there are machines that are full wave rectified machines or possibly 3-phase 6-pulse machines. I think that they have a diode out in their rectification system. What does that mean? They're shooting now with full wave rectification. When that diode went out, it's like 2 diodes went out. And so I've just lost that 3-phase part. I just have 1 phase, 2 pulses. What is 1 phase, 2 pulses? This right here. 1 phase, 2 pulse is full wave rectification, 100% ripple. It is an incredibly inefficient machine. The techniques are crazy, right? I just took a photograph of them the other day from one of the students that's out there. They need to do something about it. Because it looks, they're having to set techniques that are like 700 mass, right? What is that technique really? Divide it in half. Are you tracking with me? Because they've got all this ripple. They're creating all of these x-rays that are inefficient, that are just exposing the patient needlessly in order to get one picture, right? It's a problem. Back in the day, that used to happen, though. Our 3-phase 6-pulse machine would lose a diode would blow out, needs a diode replaced. Okay, double down on all your techniques until the engineer can come out.
Takes warning about that.
Yeah.
Yeah.
Okay. Okay. Last thing I'll talk about is the automatic exposure controlled and photodiode versus ion chamber. What we'll talk about mostly is ion chamber. Okay, I know it kind of got cut off on our slide here. Some old school texts will still call this a phototimer. In our textbook, it has a really nice neat little picture of it on page 142, figure 815. It's those 3 black dots that look like the targeting equipment for an X-wing fighter, right? When they're blowing up the Death Star in Star Wars 4, that's the X-wing's targeting system, right? Those 3, he calls it. He's got some fancy name for it in here, and I loved it. It was where is he? Oh my goodness, I got to find it now because it's so goofy. He calls it. Bear with me here. Let me pause. I liked that. So they are arranged in a triad pattern. That is important because when you make a selection of those 3 chambers, you're actually selecting to energize 3 ion chambers. And that sounds pretty freaking awesome if you ask me. But the ion chambers that you energize will be making measurements of X-ray exposure within an ion chamber. Well, what's an ion chamber? I will refer you back to last week in our discussion of the pocket dosimeter. An ion chamber that is, as ionization occurs within this chamber, positive potential or negative potential is stored in the walls of the chamber, and it can make a reading. It can read so many exposures have occurred within this chamber, right? So it's a way of measuring the amounts of radiation in something. Why would that be helpful to us as X-ray techs? Well, if I can measure the amount of radiation that's reaching this triad pattern, then I know I've got a chest X-ray. Or no, I need to keep on exposing this person until I've got a chest X-ray. It can tell my machine when to cut off. And that's why we call it an automatic exposure controller, an AEC. Like I said, some techs will call it a phototimer. That's old school stuff, right? No tech currently alive was probably still alive when phototimers were actually being used. I'm trying to think. Yeah, they were developed in 1942, right? So I doubt there's actually any real phototimers out there. Phototimer just sounds nice and neat. It sounds like photosynthesis or something. AEC just sounds stupid. But they are AECs, and they have 2 basic patterns of use. One of them may be a photodiode one, and what that means is it's causing phosphorescence within a diode. What the heck is a diode? Well, the diode's the exact same thing that's in the rectification system. Okay? It's something that only allows power to travel in one direction, right? So as the phosphorescence occurs within this diode, it powers something. It lets it know, okay, that was a hit, that was a hit, that was a hit. We have enough hits. Cut off the X-ray exposure, right? Most of what we use, though, now are ion chambers. That means they're gas-filled chambers, typically aluminum or plastic. They're thin enough to where they do not show up on the X-ray image, and they record the number of exposures that occur until a cutoff point is reached. What's important for us to recognize with this goes back to that fancy word, the triad pattern. It's important how the patient's anatomy is arranged over the automatic exposure control. Okay? Here, I'll show you an illustration of what I mean. We have this triad pattern of ion chambers, right? And I want to make an exposure of an AP, let's say PA chest X-ray, right? So I'm going to draw really goofily. Here's the patient's thoracic spine, right? The anatomy in relationship to the phototimers. Let's say this is the patient's lungs, right? You tracking with me? This goofy drawing I'm making? So considering my triad pattern, what would happen if I energized this automatic exposure control, this ion chamber? What would happen? It's only going to use this. Yeah, that's right. It's only going to use this photo cell here, or this ion chamber here. So it's going to be like expose, 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 because it's trying to get through the thoracic spine. All I need it to do is get through the lungs. So it's saying expose, expose, expose until it has enough exposure to get through the patient's thoracic spine. So what's going to be the problem if I'm looking at a chest x-ray and the exposure level was sufficient to get through the thoracic spine? How's that picture going to look? Yeah, if we were talking about film, that would be completely burned out, right? Like black like that stuff over there, right? So I have to be very aware of what ion chamber on this triad pattern I've energized, because that's how it's going to measure the exposure. So in this case, whenever we're shooting a lung x-ray or a chest x-ray for AP, we will have these two ion chambers energized, right? Because when I've got sufficient penetration of the lungs, good to go, right? Now let's think something weird. Let's talk about the lateral. Okay, so here's the same anatomy from a lateral point of view, right? Now what of the ion chambers on my triad pattern do I want to energize?
Upright.
Possibly, generally, it's this one right here. It's normally just the middle one, right? Because it's going to catch the lung the most. So, two big takeaways with this. Number one, the AEC is your friend. Your techs use it a lot, right? Number two, big point, it is not to be a crutch, right? You would not like it if your friend used you as a crutch for everywhere that you go, right? Don't use the AEC as a crutch for everywhere that we're trying to shoot x-rays, right? There's going to be times when we need to just set a manual technique. If the anatomy does not fit and fully cover the ion chamber, if there's patient care considerations that don't allow us to use the ion chambers at all, we need to be able to set a manual technique. So I say all that to say we will get more into the nitty-gritty of how the automatic exposure control works. I want you to recognize it's a major part of how x-rays are produced now, and it does have some special considerations with it. So we'll look at some of those and talk about them some in the lab. I'll make sure everyone gets a chance to think about that as Mr. Wolf is doing procedures, because that's going to be the best way to see how that plays out. Okay? But one thing you could do potentially in your clinical rotations right now is start to ask them, hey, will you point out to me how you're positioning the ion chambers for automatic exposure control? Whenever you're using the AEC or the photo timer, will you show me where the pattern set is in the preset so I can see what that triad pattern is, and I can start to think about how the anatomy is over those ion chambers? They will show you it. It's a big part of what they're doing. Okay?